Hello and welcome to Course 0 Lesson 4. Today will be a mathematics lesson on solving differential equations. A differential equation is an equation in which the derivative is a function of an independent variable. So for example, if we have dy dt, so that's our derivative, let's imagine that y is concentration. So the concentration of some species in one of our biological networks, and t is time, which we've discussed before is an independent variable. And this derivative is set equal to a function of an independent variable. So let's say 3y squared. So that 3y squared is describing how the concentration of our molecule is changing in time. That's a differential equation. Now, because a differential equation relates a function to its derivative, the solution to the differential equation is itself a function or multiple functions. And when you're solving a differential equation, the goal is to find a function that, when it's differentiated, returns the original differential equation. This is in contrast to something like an algebraic equation like x plus y equals 5, where, for example, if we have some condition where we know that y equals 2, we can then plug 2 back into this algebraic equation and solve for x equal to 3. X equals to 5 minus 2 equals 3. So again, this is solving something with numerical values. The solution to our equation is that x equals 3, whereas in our differential equation, the solution will be a function. Differential equations can be very valuable for building our models and allowing us to simulate biological network interactions and what's happening dynamically in our network. As I just described, you could, for example, show how the concentration of proteins, mRNA, or metabolites are changing with respect to time. And this matches up with a lot of biological data, time course data that we have. So this is a very valuable way to go about modeling, and we'll go into greater detail about how this is done in a later lecture, but for right now let's focus on the format of differential equations and how they can be solved analytically and computationally. Let's go through the notation for differential equations. So all differential equations will contain a derivative of a function and the function itself. And you could have something like a second order differential equation which will contain the second derivative of that function as well. Here we have a first order differential equation. And you can tell that it's first order because you're taking the first derivative of y, which is our function. And this notation here is called Leibniz notation. And that's just the way that the derivative is written for this notation. Here you have the exact same differential equation that I've just shown, however in this case it's written in Lagrange notation. And Lagrange notation designates derivative with this prime symbol. So here you have the first derivative of y with respect to t, and you also have the function written as y of t. And again, this is still a first order differential equation. I just want to show you that you can also have higher order differential equations. So in this case you have a second order differential equation, and you can tell because it contains not only the first derivative of y with respect to t, but also the second derivative of y with respect to t. Again, this is Leibniz notation. Also, I should note that it's not necessary to have the first derivative in a second order differential equation. For example, you could have that the second derivative of y with respect to t is equal to 3 over y times t. That would also be a differential equation. Alright, back to our first order differential equation. In all of these differential equations, when we're solving them, what we're trying to find is for what function y of t is the derivative of y with respect to t equal to 3 over that function times t. So we're trying to find the function that satisfies our differential equation. Let's try solving that differential equation to give you an idea of how solving these equations actually works. So we had dy dt equal to 3 over y times t. That's our differential equation, and it's a special differential equation because it's separable, which means that on the right-hand side of the equation, y and t are products of one another, so that we can separate them out in order to integrate with respect to the appropriate variable. And the way this is done, you would multiply by dt on both sides and multiply by y over 3 on both sides to get y over 3 dy is equal to t dt. So as you can see, you've separated this out into y dy and t dt, which makes it very easy to integrate both sides of this equation. And when you integrate, for the first integration on the left-hand side, first remove the constant that you're multiplying y by, which is 1 over 3, and then when you integrate y, you would raise the power by 1 and divide by that power. So you get y squared and divide by that power, so you get y squared over 2, and on the right hand side you would do the same thing. You would raise the power of t by 1, so t squared and divide by the power is 2. And then you would also add a constant, because remember, since the solution here is a function, you can imagine that when we've taken the derivative to get our differential equation, we may have lost a constant, since that constant would go to 0 when you differentiate it. So add the constant, and we can just simplify this a little bit. Y squared over 6 is equal to t squared over 2 plus c. And that is the solution to our differential equation. However, we can get a specific solution by if we have initial conditions. So imagine that we have the initial condition that at t equal to 0, so y at t equal to 0 is equal to 0. So for imagining our biological network, we're saying that the concentration of y at time 0 in our simulation is 0. We can then plug that initial condition into our solution and get 0 squared over 6 is equal to 0 squared over 2 plus c, and this would just simplify to c equal to 0. So we now have the value of our constant, and we can plug that into our final equation to get a solution where we have y squared over 6 is equal to t squared over 2, and that would be our solution in this case. So that's just one example of solving a separable first-order differential equation.
Now, while the separable differential equation was very easy to solve by hand because of a special trick to separate the variables for integration, there is another form of differential equation that you'll probably see pretty commonly in biological networks, and that is the linear first-order differential equation, which you see here. And this differential equation also has a special trick that makes it easy to solve by hand, that depends on the form that the function is written in. So obviously we have our derivative dy dt, we have a function p of t times y, and then is equal to another function q of t. So the way that we solve this differential equation is we use what's called an integration factor in a very special way. And the integration factor will always have the same form. It's always e to the integral of the function p of t dt. So let's go into an example to show you how this integration factor will help us solve a linear first-order differential equation. Alright, let's try solving one of these linear first-order differential equations. So let's say we have the differential equation dy dt plus 1 over t times y is equal to t squared. So in this case, 1 over t is our function p of t. So our integration factor in this case, which again is e to the integral of p of t dt, we would get e to the integral of 1 over t dt, and that simplifies to the integral of 1 over t dt would be natural log of t, so we get e to the natural log of t. This cancels, and you get that the integration factor is t. Now the way that we use the integration factor to solve this equation is we multiply both sides of the differential equation by the integration factor. So that's our first step, and what we get is dy dt times t plus y, because the t's cancel, is equal to t cubed. Alright, so this can simplify to the form d dt of t times y is equal to t cubed. Now once we have this form, like in the previous differential equation we tried to solve, the separable differential equation, we now need to integrate both sides of the differential equation. So again, take the integral of both sides. This will cancel and we get t times y is equal to t to the 4th over 4 plus c. Now this can simplify to the form y is equal to t cubed over 4 plus c over t, and that is our final solution. If we want a specific solution, we need initial conditions. So let's say we have the initial condition that y at t equals to 1 is equal to 0. Well, we can plug that into our final form and we get 0 is equal to 1 cubed over 4 plus c over 1, which simplifies to c is equal to negative 1/4. Alright, we plug in our specific solution and we get y is equal to t cubed over 4 minus 1 over 4t. And that is the final solution to our linear first order differential equation. And that concludes Course 0 Lesson 4 on differential equations. Now you should know what a differential equation is and how some of them can be solved analytically. However, I want to note that many differential equations are very difficult to solve analytically and by hand. So we'll go into greater detail about how these differential equations are linked to biochemical networks, and then after that we can go into the different tools that we use to solve differential equations numerically and with a computer as a very useful tool.